All right, everybody, welcome back. We are going to continue through the carbonyls chapter. We'll see how far we can get today. There's a good break point I hope we can get to, but might be trying to bite off a little bit more than we can chew, but that's okay. So last time we talked about acyl halides, and we came to the conclusion, or we came to multiple conclusions, very important conclusions, that the acyl halides are particularly reactive carbonyls in the sense of they've got a good leaving group present on the functional group, right? So when the nucleophile comes in, the door swings open, we can close the door and kick off the halide, right? What we're going to start off with today is just looking at the anhydrides. Although I could, if I had any editing skills with videos, I could just go back and just replace every time I said acyl halide and a chloride in the last video and just put an anhydride there instead. The exact same thing happens, okay? So if you go take a look at that order of reactivity for our carbonyls, acyl halides are up here, anhydrides are slightly more stable, but basically right below them, okay? And so all I should really be able to do, and if I wanted to, make 3-minute videos for you guys, excuse me for just a second, I have a little technical shenanigans here. All right, sorry about that. Kind of working in a little cramped space over here and got a lot of cables running around. Sorry, so anyway, if I wanted to just make a 3-minute video for you guys, page 923, right? And if you take a look at that, there's this figure that shows all the reactions and the transformations that we can do with anhydrides. And it should be strikingly similar to what we can do with halides. If you guys got the point yet, I think you guys have, right? They are very similar, so I'm not going to spend all that much time on this, right? But I am going to give you guys a visual explanation here because, and this is important, and I didn't want to deviate into this, but it's just bursting to get out to me. I'm going to explain how these things react, right? Now let me pause here for just a second, right? I just got, at the time that I'm making this video, I'm almost done grading the exams, and I'm going to make a separate video about that, right? But when I ask you guys to explain something, right? Explaining something is different than just looking at something and saying it's black or it's brown or it's white or it's yellow, right? That's just observing something, okay? Explaining implies a thorough understanding of what's going on, okay? Being able to describe the transformation rather than just saying this transforms into that. Why does it do it? How does it do it? When does it do it? Why does it do it, right? 5 good questions: who, what, when, where, and why, okay? Your answers should always cover those 5. Anyway, let's take a look at an anhydride here, okay? So we'll bring in whatever, right? We could pick any nucleophile that we want, with the exception of a halide, right? Going from an anhydride into an acyl halide is not that easy, actually, right? It's not that easy. In fact, it's not one of the reactions that we can do here. We can go from an acyl halide into an anhydride, but going back uphill from an anhydride is a little bit challenging, okay? But that's neither here nor there. Let's just bring in generic nucleophile. So there it is, okay? Remember, we've talked about this under basic conditions, under acidic conditions, what happens, when happens, why it happens, right? So nucleophile comes in, you open the door, right? Nothing too different at this point, okay? There's this, negative charge, okay? We open the door, we stop, we look, and whether we can close the door, okay? How do we determine if we can close the door? Well, right, do we have a good leaving group there or not, right? That's the question. So nuke, right, plus, this is green. Okay, right? Is this a good leaving group? Yes, it is, right? It's a resonance stabilized negative charge, right? Not only is it resonance stabilized, but it's also equivalent resonance structures that can be drawn. Extremely stabilizing, right? We kick off a carboxylate. Here. That's a very, very, very stable leaving group. That's why this works so well, okay? Because we have a good leaving group there, just like with the acyl halides. So every reaction that I showed you guys on the last video, if you haven't watched it yet, go do it, please, right? Like we can just swap that in right here. The mechanism's going to be identical. The products here at the end, we notice that we get a carbonyl back again. So things like Grignards will react twice with anhydrides, okay? Things like LAH, they're going to reduce this all the way down into the alcohol, right? So we reform a carbonyl here, whether it's an aldehyde or a ketone or whatever it might be, right? And then that can continue to react under those specific conditions, okay? Right? But whenever nucleophile comes in, it's going to attack. We open the door, we close the door, we kick off the leaving group. Done. Got it? So take a look at it in the book there, and just couple this back with what we talked about on the previous video there also, right? There really isn't much more for me to add about this set of reactions. Okay, it's all based off of having a good leaving group and then the mechanism that kind of dominates this chapter here, okay? We can make esters, we can make amides, we can make carboxylic acids, we can make alcohols, we can make aldehydes, we can make ketones under the correct conditions with these kind of things, right? Fantastic, okay. So let us go on to something that's a little bit different then. You guys can always tell what time of the day, or maybe you guys can tell if you're paying very close attention what time of the day I'm recording these videos, because whether I'm drinking my tea or not, right? Anyway, esters. So esters, have this basic setup here, right? Again, it's a carbonyl, right? We notice we have another oxygen there. We've got two alkyl groups coming off of the, or represented by the R chains there, I should say, all right? So how can we make one of these? Well, truthfully, there are a couple different ways of doing it, right? The best way, or maybe the most common way, I should say, is starting with a carboxylic acid, okay? Starting with a carboxylic acid. If we put some kind of trace amount of acid into this, sulfuric acid is usually kind of the go-to choice, okay? But there's a couple other things we can do. And we put in some kind of alcohol, okay? So a catalytic amount of acid and an alcohol is what we need. And what we end up doing here, well, let me change colors because that'll probably make more sense. Let me change colors here. Blue. Seems a blue kind of day. All right. So, right? And what ends up happening here is if we take a carboxylic acid, some catalytic amount of acid, and this alcohol, what we end up doing is we will make our ester, and we will end up with this. Okay. Now, if we were in class, right, what I would do at this point is just stop talking because I've already done like 5 minutes of talking. Good grief, that's a lot of work, right? And I would just say, okay, guys, figure out the mechanism, okay? And so I promise, right? I'm not just doing this for show or because I have to do this on a video, right? Really, the learning happens, right, when you guys can take my words and translate them into your own words up here. Because right now, all you're really getting is, my interpretation of organic chemistry, right? The way I understand organic chemistry through the way that I've digested and understood and studied these things, right? It's my words, right? Learning is going to happen, and understanding is going to happen when you can take my words and kind of internalize them into your own, right? Otherwise, you're just watching me, show you guys parlor tricks, essentially, right? With, well, look at this mechanism, whoa, right? Okay. Anyway, right? So anyway, stop right here and see if you guys can do this mechanism, right? If you've already read the book or whatever it might be, then, it's good practice, right? But there's nothing unusual about this, right? There's nothing unusual. What do we have? an acid with a carbonyl. Gee, I wonder if we've seen any of those kind of reactions before, right? That's the magic of mechanisms. They explain things, right? They explain things. They explain things. You guys get the point I'm trying to make, I hope, okay? So acid, alcohol, right? Alcohol being a weak nucleophile, all this kind of stuff, okay? So let's see what happens here, okay? Hopefully you guys paused and kind of worked through it. The first thing that happens is we end up making this, okay? Now where in the world did that come from? Well, what's going on here? We have to think a little bit, okay? So when we're running this reaction, practically speaking, right, we'd have some kind of a carboxylic acid. We have an alcohol, which will be our solvent, right? We typically would use this as our solvent, then we just put a couple of drops of sulfuric in there, or phosphoric, or whatever it might be, right? When I tell you guys something's a solvent, we tend to gloss over that a bit, right? But remember, a solvent is always around in the highest concentration, right? We typically don't think of solvent having a concentration, right? The question I used to ask my graduate students, which they always got wrong for the most part, is what's the concentration of water? What is it, right? And they said 1. Well, no, right? Okay, right? But anyway, the point being, right, when you identify something as a solvent, right, make sure that you guys understand what that means, right? It's there in the highest concentration, which means it's there at the highest statistical probability, maybe, if you want to think about it like this. That means as soon as I drop an acid into there, right, the first thing that's going to get protonated is the solvent itself. Now, and you're like, darn it, I got it wrong, I missed that, I didn't do that. That's okay, right? That's okay. I know what you guys are trying to do, right? And if you guys went on to protonate the carbonyl here at the beginning, that's fine also, right? Technically speaking, this is what happens though. Now, practically speaking, is this any different than H+? Well, no, not really, right? This is just a really strong acid, and the first thing that we're going to end up doing after this is protonating our carbonyl here, right? So don't worry too much if you did that. It's not that big a deal. I'm just, making a point for you guys, okay? Now watch, this is extremely important, okay? You guys catch this? Now this shouldn't be unusual, right? This should not be unusual because we're under acidic conditions, right? Under acidic conditions, what gets protonated? Well, the carbonyl oxygen does. But how many of you guys protonated this right here instead? Well, shame on all of you. Gosh, unbelievable. Why in the world would you? That's fine, right? It's fine, right? It's fine that you guys do it now, don't do it on the exam, but it's important that you recognize why you shouldn't protonate this oxygen right here. So this is the quintessential technique I can teach you guys, okay? Really, if you allow me to get philosophical here for a minute, really the reason why a lot of people tend to struggle with organic chemistry is not that the material itself is so complex that it's out there and it's difficult. I get it, right? I'm not saying that that's not the case. It's because to truly grasp it, to truly understand, you guys are going to have to stop and think about this, and really stop and think about it, not just like, well, I gave it a good 3 seconds of thought and I couldn't come up with an answer, so I'm going to, just wait for the professor to give me. I'm asking us to really critically think. Dr. H, you don't understand. My friends tell me I'm extremely critical all the time. That's not what I mean, right? That's not what I mean. What I'm talking about is when I'm talking about critical thinking, it's one of these skills that a lot of I'm not painting a broad picture of everybody, obviously, but it's one of these skills that you guys have to practice to really, really get good at it, right? And it's hard, right? It takes effort. It's a lot of work. I don't want to sit here and think critically about all this. It hurts my brain. I know. But if you guys can really do that, it's going to be such a useful technique for you guys, right? Practice it. It's just like going to the gym. If you don't practice, if you don't go to the gym every day, you're not going to get better at it. You're not going to see them gains, right? All right. So when I'm asking you guys to stop and think about something, actually do it, right? You're saying, well, wait a minute. He make this statement that I shouldn't protonate this right there. Well, why is that? Well, don't just take my word for it, right? I don't know if you guys looked up if I actually have a PhD or not. Yeah, I could just be some guy with an iPad making videos, and it's like, well, he looks kind of professional, right? But take a look at this here, right? Why wouldn't that oxygen be protonated? Fantastic question. Let's answer that, right? So the option is we have this on top, right? Or we have this down here, right? That's it. These are my two options. I either protonate this oxygen here, which is the correct one, which is the one we've been doing all along, or I protonate this here. Now I know why you guys might want to do this and say, oh look, there's water. Yeah, water's a good leaving group. We've identified this one. Yeah, that's fantastic, right? Why is this better? What does this have that this doesn't? Now remember, anytime you guys generate a charge, negative or positive, the atoms don't like it, right? Now, we have this tendency to, anthropomorphize atoms as if they have feelings, right? They don't, right? But the point being, remember, with a formal charge, it's there for you guys to look at and say, hey, wait a minute, something's unusual, something's not right here, right? An oxygen with a positive charge, it doesn't mean the oxygen's actually feeling positive. It means, hey, wait a minute, this thing has more than one bond that we typically see, right? So anyway, what's the difference between this and this? The difference is we can draw a resonance here to stabilize, right? We can resonance spread that positive charge out. No resonance structures here, okay? No resonance structures here. Here we have that pi bond bound to that atom, so we can resonance stabilize that positive charge. That's why this is a preferred method of protonating the carbonyl, because we have a more stable intermediate. This, not going to happen, okay? So, good question. It's not, like I said, it's not dumb to do this, right? It's a common thing, and I know what you guys are thinking. You're like, well, there's a good leaving group. I want to make water. That's fine. That's a good observation, right? It's a good observation, right? But be careful, because take a look at resonance structures and stability and all that stuff too, okay? Anyway. Okay, so we do this. What is the practical effect? Well, the practical effect is what we just talked about, right? Now we've got a protonated intermediate, and that carbonyl carbon's more susceptible to attack, even from weak nucleophiles, right? So let's bring in a weaker nucleophile here, okay? So alcohol, really not a good nucleophile, but under these conditions, not too bad, right? So now we open the door. Man, the one problem with drawing all these colors is I gotta keep switching. All right, and then we have this here. Cool. Okay. So now we gotta clean things up and kind of move things around a little bit here. So more of our solvent comes in. I will try and do this to save a little bit of time. Okay. So oxygen with a positive charge, more of our solvent comes in, right? Which regenerates our acid, right? So we can go through and, continue with this reaction. Okay, so here's a good place to stop and go, right? So we want to check at this point, right? Can we go and close the door? Now to be able to close the door, we have to have a good leaving group. Do we have any good leaving groups? Well, let's see. We have a hydroxide. If we kick this off, that's a hydroxide. Is that a good leaving group? No, right? So hydroxide, hydroxide. Here, if we kick this off, right, we kick off an alkoxide. Is that a good leaving group? No, right? Now, right now, we can say, all right, let's make a good leaving group. Let's do this again. Now, do we have a good leaving group? We sure do. There's our good old buddy water. Very common leaving group. All right. Let's kick water to the curb. See, this is blue, this is blue. I made that blue. This is still red, and this is blue. Okay. Now we can see essentially our ester is there, right? We just have to grab that hydrogen there. So something's going to come in. Given that it's there in the highest concentration, you can almost 100% guarantee, oops, I forgot my arrow, and 100% guarantee that it's going to be a solvent, and we end up with our product, right? Fantastic. So, from a carboxylic acid into an ester, okay? They call this a Fischer Esterification, right? I'm looking at page 925 in the textbook there. Okay? But there it is. Is there anything unusual or different about this? No, right? We start out, and remember, if we have an acid, it's typically going to be used in the first step of a mechanism, right? A good question would be, well, why is that, right? And we've answered that a couple times, but here's a good refresher for you guys, right? So why do we typically use acids in the first step, right? We take a look at our solvent. Our solvent actually comes in and does something in this reaction, right? So we have to pay attention to what solvent we use in organic chemistry, right? And we end up with an ester here. Very nice, okay? So there it is, right? Ester from a carboxylic acid. Now, what we've done, right? What we've done is this. Okay. Now we need to figure that out, right? So we've transformed a carboxylic acid into an ester. Can we turn an ester back into a carboxylic acid? And the answer is yes. In fact, we can do this in two different ways, okay? We can do this in two different ways. But hang on to that thought for just a second. We'll come back, right? Now, we talked about this last time, right? But just for emphasis sake, oops, sorry, I wanted to do this in green just to kind of maintain the colors, right? Oh my gosh, screwing up all of a sudden. Remember, if we set up these conditions, right, and this is something we talked about last time, from the acyl halide, we can put in an alcohol with pyridine to get to this point here also, right? So we don't have to just start from a carboxylic acid. Okay, we can also start from the from an acyl halide. Now, why would you want one over the other? Well, it just depends on what else you have to do and the next steps that you guys have and all this kind of stuff there also, right? So don't forget about this, okay? Okay, but let's go back to the thought here that we know how to go from one end to the other, right? Let's talk about the red arrow here. There's two ways that we can go back from an ester into a carboxylic acid. And shockingly, right? I know you guys are about to be shocked, right? Shockingly, we can either do it under acidic or basic conditions. I know you guys aren't shocked because that's all we've talked about, right? And I always tell these students, and they think, and my students, and they think I'm joking with them, right? The reason why I like chemistry is because I don't have to remember all that much. Like, oh, is it under acidic conditions or is it under basic conditions? And I do two things. Even I, right? I can remember two things. I know you guys can too, right? But this goes back to the topic that I was talking about earlier, right? It's not about memorizing organic chemistry. It's about understanding, being able to explain why. because if you try and memorize this stuff, it's just not going to work. Like I mean, you could, I guess, if given enough time and space, you guys could memorize this entire book, but good grief. Do you guys want to do that? I've got better things to do, like staring at the wall, right? You don't want to memorize this, you want to understand it, right? And so when I say under acidic or basic conditions, you should immediately say, that's all we've been talking about all along. I bet that under acidic conditions, right, we start out by protonating the carbonyl oxygen. I think under basic conditions, we start by attack of the nucleophile at the carbonyl carbon. And if you said that, and if you thought that, you guys got it, right? You guys got it, okay? So let's do that, okay? Let's really shake things up first, okay? Let's really shake things up first. This was in blue, right? And let's put this under basic conditions, right? So a little bit of water, a little bit of sodium hydroxide here, right? So see if you guys can come up with a mechanism, right? Now watch. Okay, be very careful. We're going to end up with an O- here, right? Okay. So we're under basic conditions. We've got a carbonyl group. This is a fantastic nucleophile, a really powerful base also, right? Both of those ideas are going to be important, right? We've got a carbonyl group. That means obviously attack at the carbonyl carbon is going to happen first. We open the door, we close the door, right? So let's do that. I guess I'll move down here since I ran out of room. Ooh, hello. Okay. OH, OR. Okay. Well, we opened the door. Now we got to close it. And so the question should be, well, do we have a good leaving group? The answer is not really, right? Ooh. If we close the door, we kick off an OH, that's back where we started. If we close the door, we kick off an OR. That's not too far away from where we started. So, whoops, there it is. So, do we have a good leaving group here? Well, no, not really, okay? But here's something I didn't really put under there. Typically, we have to do this under heat, okay? We typically have to do this under heat, and this is why. So if I ask you guys the question, why do we have to do this under heat? This would be one reason why we do this, right? Because we really don't have a good leaving group here. So if we don't have a good leaving group, we have to give it some oomph for something to leave, right? We have to give it some energy. We have to get over that hill, right? We have to get over the hill to get this reaction to continue to go, right? So remember, if you can't try subtlety, you try brute force, right? So we basically just heat this up. Green, red, red, and red, okay? With me? What functional group did we make? Oh, geez, we made a carboxylic acid. Okay, we're done. Life is good. Be careful, right? Boy, I don't know, some days computers and me just don't get along, okay? So we made a carboxylic acid and we are under basic conditions. How long is this acid going to hang around? The answer is it's not. Because look, now this is something you're gonna have to imagine you're floating around in this reaction. You just kicked off an extremely powerful base. So proximity, right? This extremely powerful base is right next to an acid instantly, right? For all intents and purposes, right? Instantly, this is going to do an acid-base reaction. Remember collision theory, which we talked about, quite a while ago at this point, right? Just talks about that things have to physically be close to each other for, something for the reaction to happen. right? And so this is an example of that, right? We've got something right next door, a base, right? So what we end up doing, oh, let me draw this the other way. So what we end up here is with an alcohol, right? And so this might be another reason, depending, right? This might be another reason why we heat this up. If we have some kind of short chain alcohol, then if we heat this up, we can basically boil this out of solution, right? And that will drive this reaction forward via Le Chatelier's principle, right? So now, if we have a long chain alkyl group here, then that's not really practical. But if you kick off a short chain alcohol, that's definitely something you can do, okay? But we end up with a carboxyl 8, okay? But that's not what I asked. I asked to make a carboxylic acid. So when you do this reaction under basic conditions, you end up with that product first, and then you got to come back and do an acid workup, okay? You come back and you do an acid workup, and there you get the product that you guys want, okay? So just like what we saw with LAH and other of these strong bases under strongly basic conditions, you typically always have to come back and do a acid workup at the end of this, okay? All right. So real quickly, we're going to go through the last idea here, right? This video has gone a little bit longer than what I wanted, but that's okay. Let me give myself some nice fresh space here. So we talked about under basic conditions. Now we're really going to change things up and go under acidic conditions. Whoops. Got a little bit too happy there with my positive charges. Okay, if I do this, then we will end up at a carboxylic acid also, okay? So under acidic or basic conditions, we will end up at a carboxylic acid. Can you guys do this mechanism? The answer is yes, right? We're under acidic conditions with a carbonyl group. What is going to happen first? Well, I think you guys know at this point, right? So, okay. Why do we need to do this first? Why does this happen first? Why does it go to that oxygen? Why, right? What is the consequence of it doing that, right? Let's see, this is in red. This is in red. Okay. Very similar to what we saw previously with the esterification, right? So we do a little bit of cleanup here. Bring in some more water, because water is always around. For better or for worse, depending on what you're trying to do in the lab. Water is typically always there. Okay. Do I have a good leaving group to close the door? No. So I got to make one. How can I make one? Well, I've got acid around here, right? I've got H plus around. So let's H plus it up. We'll carry this down here. Oof, that looks terrible. Ugh. Even me and my poor artistic skills, I don't like that, but that's okay. We'll deal with it here in just a minute, okay? So moving right along, zooming right through. Okay. And last, but certainly not least, get rid of that positive charge on the oxygen up there. Fantastic. There it is. Okay. Attack the carbonyl oxygen attacks the acidic hydrogen, which makes us more susceptible to nucleophilic attack. The attack happens, we shuffle protons around, we close the door, and we clean up once more at the end to get to our product. That's the mechanism, right? This is the quintessential idea of carbonyl chemistry, okay? So it didn't get quite as far as we wanted to, but pretty darn good, okay? So we learned about how to make esters, and we learned about how to turn an ester back into a carboxylic acid. Next time we'll finish up, we'll have a couple more reactions to go, and we will keep making our way through this. I will see you guys in the next video.